We discussed about autoencoders in the last session, and autoencoders are all about encoding itself, right? So the input is passed through the encoder decoder arrangement, and then the output is nothing but uh, input itself, or you learn the mean square error between the prediction and the input so that you gradually learn how to reconstruct the input itself. Okay, so that's the key idea. And once you have the learning done, so we cleverly used the latent space to reconstruct. You only use latent space plus the decoder so that you kind of reconstruct the images back from the uh, latent space. But the issue we faced there, or the issue we kind of discussed there, was can we control the latent space? Because it was all over the place for autoencoder and it's very difficult to predict exactly. There's no precise control on the prediction. That's what variational autoencoders is going to solve for us. Okay, so what is variational encoder? So this is a probabilistic spin on the autoencoder. So it's an interesting idea where you kind of add a flexibility or control on the latent space. So you basically parameterize the latent space because once you have the parameter, you can control it, right? So that's the idea. So everything remains same except that in the case of autoencoder, this was one solid block, which is the bottleneck, right? That is gone. So now let me explain this. It's actually a very interesting concept. So what you're going to do is the encoder is no more going to predict the vectors or not going to generate the vectors in that sense, but it is going to predict the mu and sigma, so mean and variance of a distribution. So it's no more predicting values as it is. The encoder is no more giving you values, which is the usual case for any neural network encoder decoder arrangement. Whatever you expect is a set of values or vectors here. Instead of that, it's going to predict the mean and variance of the vector. Okay, so that's a key factor, and we assume a distribution for this. So this is basically, if you remember what we are trying to achieve here, let me explain that the holistic sense. So let's say you have the distribution, the two-dimensional distribution, dimension 1 here, dimension 2 here of letter 0. So let's say this is the distribution. What we are trying to do here is parameterize this distribution into a mean and Gaussian. So you represent the mean value by a single value somewhere here, and the variance, the two-dimensional variance here, which can cover up that distribution. So by defining these two, you make sure that whatever 0 is kind of restricted to this. And to make it more holistic, we assume a distribution for these points as well. And that distribution is typically assumed to be a Gaussian distribution, which is defined by its mean and its variance. So, or more specifically, it will be a kind of a normal distribution with 0 and 1 is the aim, 0 mean and variance of 1 unit variance. But we can generalize it to be like a Gaussian. I think N is the wrong way to define it. G is better. So Gaussian of mean mu and variance sigma, and that these mean and variance are predicted by the encoder. So encoder is no more giving you vectors. That's a key factor. It will predict you scalar values for each input image, which is a mean and a variance. And now using this mean and variance, I will create a Gaussian. Okay, so in this space again, I'm going there. I'll create a Gaussian. It may be a smooth. Gaussian is always smooth, right? So you have a center and then you have a Gaussian, which is kind of shown by this shaded region. So that's the distribution of your latent space corresponding to a single input. Let's say input of 0. Input of 1 will have another distribution. Input of 2 will have another distribution. 3 will have another distribution. Now, the next step is the decoder will pick up a point from the same distribution. Let's say 0 is the input, so it has this distribution. It will pick up a point, let's say this point, and that point is passed to the decoder. So it will create a vector or a point, sample a point from that Gaussian distribution, which is learned here, and then reconstruct it back to the image. So there is a decoupling here. This is not a small vector flow here. You have the encoder predicting the mean and variance of your Gaussian distribution, and from that distribution you sample a point. So this is a sampling process which is happening here, and then that point is used to reconstruct the image back. So that's why it's called variational autoencoder, because you are defining a mean and variance for your distribution. Okay, so you have control now. You have parameterized your vector, the bottleneck, the latent space, into a Gaussian distribution with a certain mean and a certain variance. Okay, so that's a very beautiful idea, and this idea was proposed by Kingma, and Kingma is also known for the idea of Adam optimizer, so adaptive optimizer with momentum, right? So it was proposed by Kingma because the same person is behind this variational autoencoder idea itself. Don't forget the ultimate objective. The objective is to control or parameterize the latent space. And in this case, latent space is modeled as a Gaussian distribution. Okay, so that's the idea. Okay, so reiterate it again. Instead of a typical encoder latent space decoder, which is a kind of a continuous space, the latent space is approximated to be a desired shape. Example, Gaussian. Okay, the variational encoder works in 3 steps. The first one is the encoder predicts the mean and variance. The second step is a latent vector is created by sampling from this space created by the Gaussian. Okay, so the latent space is Gaussian here, which is created by the mean and variance. So you just take one sample point, for example, and then decoder is taking the role there. It takes that point and reconstruct the image. And again, the loss function here. So how do you control the mean and sigma, right? So the loss function is two loss functions here. One is of course the L2 norm between x and x bar, which is as similar as to the autoencoder. The second is basically the most important aspect is to enforce this distribution, whatever this to be goes in. How do you do that? And that's something which is interesting. We'll discuss that in this slide. But before that, let me explain that process again so that it's very clear to you. So encoder, decoder will have a single point which will predict the mu and sigma for this point. You use the sigma and mu to create a Gaussian. So you have a distribution. So no more a point, it will be distribution. So essentially, if you have another point, it will be somewhere in this distribution. This point is somewhere in this distribution. So everything will be in this distribution. Okay, and then you sample from this point. So this distribution, you sample the points and then the decoder is done. So this is that entire process. You start with the point or the vector, you convert that to a distribution, and then you sample from that distribution to the image. So you have a distribution which is playing a role, and that is controlling the latent space. And that control is important for us because that control will help us with some sanity to reconstruct the image, because now I can control the latent space, and through that control I can control the output image. Okay, so that's the holistic idea. Now let's go to the loss function. Okay, so this is tree, because so far I've not discussed how are you saying that this mu and sigma will be a Gaussian distribution, right? So it is just two numbers which are predicted, and that need not be within the Gaussian distribution. It can be anything, right? How do you constrain that mu and sigma is going to help you with a Gaussian distribution? So the idea is very interesting. The two loss functions, as I said, one loss is already we know the typical autoencoder, which is between these two, the L2 norm between those. The second one is the key factor. It is something known as Kullback-Leibler divergence. Again, I'll give a link to the beautiful explanation of the KL divergence. But if in case you want me to discuss a deep dive on KL divergence, please let me know. I will maybe next week will add a separate video on that. Okay, but this is a beautiful technique. And what is this technique about? The KL divergence is a technique which is used to identify the similarity between two different distributions. If I have a data distribution 1, I have a data distribution 2, I can find how similar are they. And this is what helping us to enforce the Gaussianity on this mu and sigma. So this is a loss function or the divergence that we are trying to achieve. So this is created, this Gaussian or this distribution, we don't even know this is Gaussian, this distribution is created by the mu and sigma from this, and then you pass it through the Gaussian formula. So the Gaussian formula, if you don't know, it is this x minus mu square by 2 sigma square. Okay, 2 pi sigma square to be exact. Okay, so x is the point values, mu and sigma point values in the sense indices, and mu and sigma are the values which are derived from this. So these values are passed to this function, and that will create a distribution, and that is compared against a normal distribution, which is again a Gaussian distribution with zero mean and unit variance of 1. And this is important, this divergence calculation is important, this because this is where we are enforcing the distribution to be moving towards the normal distribution or this Gaussian distribution. Okay, because you don't really have control on mu and sigma, and this mu and sigma can take any values and it may not converge to a good Gaussian distribution. But the scale divergence is nothing but a similarity check. So how similar is your distribution with a given distribution, ground truth distribution? So the ground truth distribution is a Gaussian with zero mean and variance 1, which we call as a normal distribution. So that's your ground truth. So you're trying to use this mean and sigma to move towards or to be as close to the normal distribution. So this function, this KL divergence is what enforces that nice Gaussianity on your prediction. Okay, so that's the key factor. So two losses, this is already known to you. The second one is a KL divergence between this predicted distribution to a ground truth normal distribution. Okay, so that's a key factor. It's a very important thing to understand. And in the case of a Gaussian and a normal distribution, the KL divergence is very simple, which is a standard expression which is shown here in terms of just the sigma and the mu. Okay, so it's a pretty much analytical expression which can be solved using the code, right? So there's nothing fancy. Each time mu and sigma is changed, you have this KL divergence calculated, or the Kullback Lebler divergence is calculated. Okay, so that's a key idea. So as I said, for in-depth understanding of KL divergence, these two videos will help you. Very nicely explained. I highly recommend you to watch in case you want to do a deep dive. Otherwise, you just consider this as a measure of how similar two distributions are. So you define a ground truth distribution, and your predicted distribution is forced to look like the ground truth distribution. Okay, so distribution, when you say, don't get confused, is it's nothing but uh, again a function, right? So a Gaussian function I already explained to you, it is x minus mu square by 2 pi sigma square. Sigma and mu are known to you. X is the value indices you can range from. Let's say if you have 1000 vector, you can range it from 0 to 1000. So that's this x value. Okay, so based on that you get a value. Of course, it's two dimension, means you will have this multiplied by another one. So into y, you can say y minus mu squared by 2 pi sigma square in two dimensions. This multiplied by this will be a 2D Gaussian. Okay, so the idea is simply that. So two loss functions, one for, so this ensures that the image is reconstructed very similar to the ground truth. This guy ensures that this distribution is kind of confined or going towards a normal distribution. Okay, so through these two approaches, what we achieved, one is like we achieved a compressed representation, and not in a vector form but in a more controllable mean sigma form or a distribution form. And once you have a distribution, literally you can sample any points from that distribution. So that's the holistic idea that we are talking about. Okay, and I just want to show you the training for variational autoencoder, again derived from this beautiful YouTube video. So you can see here the distributions are no more like distinct clusters. They look like a Gaussian, which is like this shape, right? So you can approximately see the shape. It looks like a circle almost. Okay, and that's the holistic idea. Okay, so this is uh, pretty useful. Now let me show the reconstruction part or the inference part. So let's say I again how I think I don't have a pause here, which is rather surprising. Okay. Anyway, I'll explain this first, and then we can. So we have a Gaussian distribution for 4, which is identified here. So all the points of 4 will be inside this. 5, which is all the points of 5 inside this. Now, if I move from this point to this point, you can see a smooth transition from 4 to 5. And that's the beauty about variational autoencoder. There's no confusion like in autoencoder. So you can see here. Of course, a point here will create a new number, and that's what image generation is all about. Right now, we are getting innovative. So you're creating something which is there, not there in the original space also. But as long as you are in this distribution or this distribution, it will be either 4 or 5. So 4 here, as you move, it becomes some random number or some random shape, and then as it becomes closer to 5, it becomes 5. So this is a beauty. So once you have a fully trained variational encoder, you can throw away the decoder. You can just play with the throw away the encoder rather, and play only with the decoder part, and you just sample the points from the Gaussian distribution for any of the non inputs, and you can kind of reconstruct that input perfectly, variations of that input perfectly. Okay, so that's the idea. Now there is a problem. So this we already discussed. There is a problem here because you can calculate the loss function. That's beautiful, but you need to back propagate, right? But that there is a sampling process which is happening here. You are basically sampling this z from this Gaussian distribution. That is actually not a function, right? It's actually a process. So you won't be able to back propagate. You need to pass the gradients, right? So you need to update the gradients. There is no gradient for a process. So you need to convert this process into a function. So that's the solution. So you parameterize the sampling. So you need to kind of come up with the sampling as a function, not a process. So this is also easy. So this is a simple change here. So this is now changed to this entire process of the distribution plus sampling is converted into a function now. This epsilon is nothing but a normal distribution with 0 mean and variance of 1, and sigma you already know is predicted from this, and mu is also predicted from the encoder. So basically the encoder will predict mu and sigma, and then you use this function. This is now a function because epsilon is a Gaussian function. Sigma is basically a scaling operation on that function, basically amplitude scaling of the Gaussian function, and mu is the translation of that function. I'll explain this using a figure. Okay, so let's assume this is your parameter, so this distribution, and originally you want to sample from this distribution. Okay, so instead of that, you can actually consider this normal distribution 0 1, and you assume this is the equivalent point of this. Okay, so this point, if you see this goes in, the first step is you scale it by your sigma. So which means the size, the scaling, the variance is now exactly the same. This unit variance is converted to the variance of your distribution. So this variance and this variance is same. Now you need to add this mu so that this guy will shift to this, so they will overlap. So that's it. So now you see I got this sample point which was supposed to be sampling from the original distribution, which is a process. I cannot use that because I need to back propagate. The gradient has to be calculated. Now that is converted to a symbol function here. Epsilon is a Gaussian, don't forget. Epsilon is a Gaussian function. Sigma and mu are just scalar values. So you have a function here, and moment you have a function here, you can basically back propagate the loss. So that's the idea. Okay, so this is a code. This will make it very clear. So this is a typical encoder, typical decoder, and then that's the part where you kind of, let me explain this clearly to you. So you have the mu and variance predicted here, and we typically take the log of variance because similar to the earlier case, I think we discussed this during object detection. the log conversion will kind of keep values within certain dynamic range. Okay, so that's the reason why we do this operation. And then you kind of calculate the sigma, and then you calculate the translation. So this is basically that function I was talking about. Those, this is epsilon, or the uh, what you call the normal distribution, and it is scaled by sigma added with mu, which is what we get the point z, and that z, all of these are output from the encoder. So now you see decoder just takes, so I think this will help. So the encoder will take in the input and gives out the z value, which is calculated here, and the mu and log variance, which is not really used, but it's good for us to use it during the inference part. And then the decoder will take this z in and reconstruct the image back. This decoder output will be the same size as your input x. Okay, so that's the idea here. So controlled reconstruction. So that's what I was talking about. Again, if you think of the 2D representation, so by if I represent my parametric space as 2D, or the Gaussian distribution space as 2D, by varying the first and second dimension, I'm able to kind of reconstruct all the possible images. So you see here, all ones are in this region, all zeros are in this region, and similarly, I mean, you can basically consider all the scenarios here. So you take any sample point. So this, if I take a point here, it will be 9. If I take a point here, it will be 8. If I take a point here, it will be somewhere, I mean, it's not a useless value in that sense, but it's somewhere hybrid between 6 and 9. Okay, so there is a control now is what I'm talking about, because earlier it was cluttered all over the place, if you remember the autoencoder, but in the case of a variational autoencoder, it's kind of coming together to a more controlled way of doing the reconstruction. And there's another example. These are taken from the paper, the first paper on variational autoencoder. Here, this is a facial image, and you can actually see the emotions are controlled, uh, or cluttered, or clustered rather, in the space in a nice way. So if you want a happy space, you sample at this section. If you want a sad face or something like that, you sample at this section. Okay, so that's the scenario. So all this I'm talking about is just the z space. So z1 and z2 are the two dimensions in the z space. Okay, so staying at the z space and using the decoder, the learned decoder, I'm able to reconstruct the image, and that's what we want, right? So our journey started with getting into that latent space, then the controlling of the latent space, and now we are talking about, once you have a control latent space, you can reconstruct the image. Okay, so that's uh, the journey that we have been so far. Okay, so few issues, of course. Autoencoder plus variational autoencoder, the input is something like this, but if you see the output, they are blurrier and low quality. And similarly, the CIFAR dataset, which is a natural image dataset, it has over several classes. If we just consider the 10 classes and reconstruct, train on that, and reconstruct the images, it's their images are reconstructed, but not of very high quality. And this was one of the problem, and this was one of the motivation why we moved to something known as generative adversarial networks, which are known to produce high quality, high resolution images from all the concepts that we discussed so far. So we'll go there in short time.